So here in this video we're going to learn about esters, another derivative of carboxylic acids. And here's one on the right hand side. This is an ester, and this part of the molecule here, this oxygen that is bonded to two carbons, is the ester link. That's called the ester link. This part of the molecule on the right came from an alcohol, and this part of the molecule on the left came from the carboxylic acid. And when we react them in the presence of concentrated sulfuric acid, then they react together, and actually the part that was from the acid is this part here, and the part that was from the alcohol is the part on the right hand side. But in terms of naming esters, it's actually beneficial if you think of this being the link there, because then what you can do is you can name the bit that looks like an acid. Right, so we've got two carbons on the left hand side here, and if the oxygen in the ester link had a hydrogen on it, it would be ethanoic acid. But it's lost its hydrogen, so we can name this part of the molecule ethanoate. And this part of the molecule that was a bit of the alcohol molecule is going to be methyl. And when we're going to name the ester, we put the alcohol bit of the name first, and we put the ethanoate, the acid bit of the name second. So this ester here would actually be methyl ethanoate. Like that. Okay, so that's roughly what esters are. So we've covered that lesson objective off already. We're going to have a look at some esterification reactions, like the one we spoke about briefly there. And then we're going to look at some uses, 4 uses of esters, before we look at the hydrolysis of esters. And hydrolysis, you might remember, means to break down the molecule, usually using water. And then fats and oils, which are esters in fact. We're going to have a look at those before we finish off with a quick tour around biodiesel. So we'll briefly run over formally what we did on the last slide about what are esters. And esters are made from carboxylic acids. So let's write a generic carboxylic acid with one alkyl group attached to a alcohol group. I'm going to write the hydroxyl group there in red, because that's going to be the bit of the molecule that moves. And so the carboxylic acid is going to react with an alcohol. We might have another alkyl group, but this time attached to a hydroxyl group, of course, with an alcohol. And so when they react in the presence of concentrated sulfuric acid, then you're going to get your ester. Okay, so our ester consists of our original carboxylic acid alkyl group, and we've still got our carbonyl group there, and we have our ester link formed, which links up with our alkyl group that was part of the alcohol molecule. So that's our ester with the ester link, but we've condensed out the OH from the acid and the H from the alcohol, and we can write it like that because they're going to come together and make a water molecule. So that's why we call it a condensation reaction, because we drop out, we eliminate that water molecule, part of which came from the alcohol, the other part came from the acid. And last thing to say is that the functional group of the ester is that bit there, and we write that if we want to write just formulas, it's just COO. So let's name a few esters. We're going to start off with the carboxylic acid, and then we're going to react that with an alcohol. We'll work out its name, and then we'll write down its formula. So firstly, if we started with ethanoic acid and ethanol, what we do is we take the eth part of the alcohol, that's it there. We're going to add an YL to it to call it ethyl, and then we take the ethan part of the acid. We forget about this oic acid part of the name, and we add O8 to it, and then we just join them up together like this, ethan O8. Okay, so this part has come from the alcohol, and this part has come from the acid, and here we've got it written in blue and red as well. So this is the ethanoate ion, and this is the ethyl part. That the red colour denotes it came from the alcohol, and the blue colour denotes it came from the acid. So there's how to name the first ester. Let's have a look at another one. This time we're taking ethanoic acid and we're reacting it with methanol. All right, so the meth part comes from the alcohol. We start with that when we're naming it. So there's the meth. We add the il, methyl, and then the ethan part comes from the acid. We scrub out the oic acid and we add 8 instead. So there we get ethanoate, and that's our formula again. Let's try another one. So this time we've got propanoic acid and ethanol. All right, so we start with our alcohol, eth. There's eth. We've added il to it. It's ethyl, and then we move over to the acid. There's our propan. We get rid of the oic acid. We add O8. And we've got ethyl propanoate. And one more, butanoic acid and propan 1-ol. So we've got the prop plus the il makes our propyl from our alcohol, and then carboxylic acid gives us our butan O8 part of the ester name. So there we have it. There's how to name esters. When we are drawing structural formulas of an ester, right, it's best to start with the acid end of a molecule. So if you were to draw this last one here, propylbutanoate, first of all I would draw my ester link. So that would be like that. Then I'd do my acid part, right, which is this part here. Should have drawn this in blue really. Let's switch over to blue. And so that's my propyl bit. So I'm just going to write CH3, CH2, CH2 there on the end of it. And then I'm going to do in red the bit that comes from the alcohol. So we can quickly write that. CH2, CH2, CH3 in there. Good. Right, we'll have some more practice with reactions now, I think. So esterification reactions are just those reactions that give us esters from carboxylic acids and alcohols in strong acid catalyst. But sometimes you see a question which starts off with the ester and requires you to determine which acid and alcohol it was made from. So let's do a little example like that. Let's write out propyl methanoate, propyl methanoate. So let's start off with the propyl bit of the ester, and the propyl bit, you'll remember, it comes from the alcohol, and I like drawing the alcohols on the right hand side. So let's draw our 3 carbons of our propyl group on the right hand side, like so. So this is hydrogen. We'll draw the hydrogens in for completeness. And then on the other side of this carbon is going to be our ester link, which is like this to another carbon. And then the methanoate part is the part of the molecule that came from the acid. So we want our carbonyl group came from the acid, and it's meth, which is one carbon, and there we've written it already, so we've just got one more hydrogen to draw in there. So that's our propyl methanoate. And let's practice the question that says, okay, there's propyl methanoate, which acid and alcohol did it come from? So, well, we're going to have a look at the split. Okay, so we're going to split it here, and on the left of that is the acid part, and on the right of that is the alcohol part. And so then we can draw out the acid, which is the hydrogen and the carbonyl group, and the acid ended up losing a hydroxyl group to the water that was eliminated, and then we're just going to draw out the alcohol group. We've got this, that oxygen is going to be bonded to just a hydrogen, and then the carbon, the propyl group, like so, with our hydrogens on the ends of these bonds. There, and you would have to add water to that, plus an acid catalyst, in order to make that happen. And the acid catalyst is to facilitate the reaction mechanism, and the water is to provide the OH and the H groups that add on to the acid and the alcohol. Okay, so there's another little esterification reaction, one in reverse that we've done. We're going to move on now to uses of these esters. And there are 4 main uses of esters. There's lots of uses of esters, 4 that we want to be familiar with. I've got some pictures here to illustrate some of them. We've got some PVC windows here. So this PVC is hard and inflexible, as you'd desire if you were making window frames. But the same polymer, PVC, can be made into cling film. So they're both PVC. This one's PVC, this one's PVC. But in the case of cling film, we've got plus 18% of an ester. And the ester that we add is called a plasticizer. Plasticizer like that. And so many of the flexible plastics that you'll see, including rubber hoses for example, would include plasticizers. Now the thing about plasticizers is that they're quite volatile. They're not chemically bonded to the polymer molecule, and so they actually evaporate over time, and that's why old plastics that were nice and flexible when they were new become brittle and crunchy. Okay, so plasticizers, one use. Let's have a look at this. We've got some perfume here. Lots of esters have nice smells, and so they are often used for perfumes. And what's more, they evaporate quite readily at body temperature, and so that means that when they evaporate, they can make their way over to somebody else's nostril, so they can smell your perfume. So the fact that they are volatile and they often have nice odors is what makes them good for perfumes. Okay, that's number 2. Let's have a look at another one. We've got printing inks here. So in the case of printing inks and pigments of any kind, they are good solvents. And as well as printing inks, esters are used in glues as well, because the solvent evaporates and leaves the pigment or the glue molecules behind, which is the when it dries, and that's by design. Okay, that's, what's that, 1, 2, 3. We must have one more. Okay, we've got, oh yeah, in terms of aromas and tastes. Like we said before, lots of esters have nice smells and tastes. For example, benzoyl ethanoate, this one here, is what you smell when you smell jasmine tea. When you smell orange, it's octyl ethanoate that you're smelling. Pineapple is ethyl butanoate, cinnamon is ethyl cinnamate, as well as aldehydes as well. But this is what gives it a lot of the aroma. But let's differentiate between aromas and tastes. For example, and it might be a different ester that gives something the taste compared to the aroma. For example, in pineapples, whereas ethyl butanoate gives the aroma, the ester that gives that pineapple its taste is pentyl pentanoate. Pentyl pentanoate, like so. Okay, so there's 4 uses. The last one, food flavorings and odors, and glues and inks and paints use esters as solvents. The smell of a perfume is an ester, and plasticizers are made out of esters. Okay, yeah, we're going to look at hydrolysis of esters now, and let's start off by reminding ourselves what hydrolysis means, and it just means to break down. And when we're going to break down an ester, it's likely we're going to break it down into its constituent acid and alcohol molecules, and that's sort of what happens. But there's 2 ways in which we can hydrolyze an ester. One is called acid hydrolysis, and the other one is called alkali hydrolysis. When we do acid hydrolysis, that's with dilute acids. It doesn't have to be a strong acid. Then we're going to get our carboxylic acid. We're going to get our carboxylic acid and our alcohol molecule. But when we do alkali hydrolysis, it's not quite the same. We still get our alcohol that we started off with when we made the ester, but we're going to have our salt, which, let's say we were using sodium hydroxide as our alkali, then you would have a sodium salt. So sodium carboxylate, depending on which acid you had. So if it was ethanoic acid, you'd have sodium ethanoate plus your alcohol, whatever other alcohol you had. Okay, so that's generally what happens, and this difference here between acid and alkali hydrolysis, i.e. what the slight difference in products that you get, is worth remembering. So let's have a look in a slightly bit more detail at acid hydrolysis. So let's have a little subtitle here, acid hydrolysis. And we're just going to do a little example of an acid hydrolysis reaction. So we're going to break down an ester. Let's say we're going to break down ethyl ethanoate. So that will be CH3, COO, C2H5. That's ethyl ethanoate. We have to add some water in, of course. Right, it's the opposite of a condensation reaction, and it's an equilibrium reaction, so it doesn't happen doesn't go all the way. If you do this reaction, there will be 4 chemicals in the reaction mixture, the 2 reactants, the 2 products, and you will need a dilute acid, and you will need to heat it under reflux to make it happen. And so in this case, you're going to make ethanoic acid, which is CH3, of course, COOH, and you're going to make it ethanol as well. So that's C2H5 OH, and let's just remind ourselves that our water molecule is going to be used to break up the ester, and the OH part, the hydroxide part, is going to join the acid, so that's going to become this O and this AH, and the other hydrogen part of the water molecule is going to join on and complete the alcohol, in this case ethanol. Okay, and so you just need to remember that to make that happen, we need to heat under reflux with a dilute sulfuric or hydrochloric acid catalyst. So that's acid hydrolysis. Let's have a look at alkaline hydrolysis. So alkaline hydrolysis. And the thing about alkaline hydrolysis is that it is a complete reaction and it's quicker. So we don't get the equilibrium mixture, we get just products made. So let's do a little example here. Let's do ethyl ethanoate. So ethyl ethanoate is CH3, C00C2H5 like we had before, but in this case what we're going to do is we're going to add sodium hydroxide. Okay, that's not a catalyst, it's a reactant, but again we're going to reflux with heat, obviously. But it's, as you notice, I've written an arrow there rather than an equilibrium sign because it goes all the way. And what we do is we make the salt. So we're going to make sodium from the sodium hydroxide, and the anion is going to be ethanoate. So let's draw our ethanoate ion out again, CH3COO, and our sodium from our sodium hydroxide makes up the rest of that salt. And of course we've got the same alcohol coming out, we've got ethanol coming out, C2H5OH, and like we did with the acid hydrolysis, let's just track a couple of the reactants. So our sodium here, I'm just overtyping it in red, goes to join the salt, and our hydroxide of our sodium hydroxide splits up, and the oxygen goes to the salt, and the hydrogen completes the alcohol. And if you wanted to make the acid out of your salt, first of all you would separate your two products, potentially by evaporation and crystallization or distillation. You could distill off your alcohol. And then what you would do is you would add some hydrochloric acid, and you'd get a reaction which gave you your acid, your mineral acid, as your carboxylic acid, because that's the weaker acid. So you'd have CH3COOH. And the sodium would go off with the sodium chloride, like that. So that's how you would get your acid back from that alkaline hydrolysis there. Okay, so let's move on to fats and oils. And why might we have fats and oils in a lesson on esters? Well, the fact is that fats and oils are esters. So they are esters. And if they are esters, they're made up of acids and alcohols. Okay, so the alcohol that all fats and oils are made from is glycerol, which has the IUPAC name of propane 1,2,3 triol. So let's write that down. So we're going to have propane 1,2,3 triol. So it's got 3 hydroxyl groups, and the fat that the acid that it's made out of are fatty acids, and these can vary, of course, to make the different fats and oils. So the fatty acids are going to have generally have the structure of any acid. So we've got our acid group, But the fatty acids are the R group on the fatty acid is going to be long. It's going to be about 18 carbons long, and they can be saturated. Right, i.e. they don't have any double bonds, or they can be unsaturated, in which case they do have a double bond. And the most common one is stearic acid. Stearic acid, and that's made up of a 18 carbon saturated fatty acid and an 18 carbon that's a saturated one and an 18 carbon unsaturated. So it's a mixture of two different acids that make up the fatty acid. So there's our acid and alcohol. Let's have a look at the reaction that takes place in order to make fats and oils. So let's draw out our propane 1,2,3 trial first, shall we? So we're going to have propane, so we've got 3 carbons. Let's draw it vertically. You'll see why in a minute. And it's trial, so we're going to have 3 hydroxyl groups. We can have them coming off this way. And as well as that, we need a couple of hydrogens here, just one in the middle to make, and a couple on the end. So that's our propane 1,2,3 trial, and in brackets let's just write the common name for it, so it's glycerol. And what we're going to do is we're going to react that with our fatty acids, and we could have 3 different fatty acids, for example. Let's draw 3 different fatty acids. So the difference is going to be just in the alkyl group. The acid part is going to be the same. So that's 1 fatty acid. Let's draw a different fatty acid and a 3rd fatty acid. Okay, when we react them together, we're going to make our ester, which we're going to call a triglyceride ester. Let's see what we've got. Let's start with our backbone first. So we're going to have CH2, CH, and CH2. Now the ester link comes next. There's our other ester link there, but of course in this reaction the alcohol loses its hydrogen and joins onto the acid group, carbonyl group of the acid. So we can draw those in as well. And the last thing to do is to put on our 3 different alkyl groups from the 3 different fatty acids, like so. Of course we're going to lose 3 water molecules. Let's just show you where they came from. So our hydrogens that were on our 3 hydroxyl groups of our propane 1,2,3 trial have gone, and they've reacted with our OH groups of our fatty acids, and that's what made our 3 water molecules there on the right hand side. And let's just highlight this ester link. That's our ester link, and we've got 3 of them. And what we've made there is a triglyceride ester. Tri for 3. Triglyceride ester, like so. So let's summarize by saying that fats and oils are triglyceride esters, and triglyceride esters are esters of our propane 1,2,3 trial and 3 fatty acids, which could be the same or could be all different. Now fatty acids, these fatty acids molecules here, they could be saturated or unsaturated. When they are unsaturated, they tend to be oils, and when they're saturated, they tend to be fats. Fats are generally solid at room temperature and oils generally liquid at room temperature. Because of the van der Waals forces, the unsaturated ones with the double bonds don't get as close to each other as the saturated ones, and so that affects the van der Waals forces. And that's about it for fats and oils. So just like we spoke about hydrolysis of fats and oils before, when we spoke about acid hydrolysis and alkaline hydrolysis, well, alkaline hydrolysis, so let's write that up here, alkaline hydrolysis of oils makes soap. That's where soaps come from. So let's start off with a fat, which might be a fat in beef fat, for example. Most soaps are made originally from beef fat. So let's draw out our triglyceride. So we're going to have a 3-carbon chain along the left. Let's have put our nominal hydrogens in there. We're going to need 3 ester links. And then we're going to need 3 carbonyl groups. And then we're going to need the rest of our alkyl group of the fatty acid. And so in beef fat it's about 16 carbons in a chain linked to a methyl group. Same again on this one. So it's 18 carbons altogether, which is what we mentioned in the previous video. So there's our fat, right? And what we need to do is we need to heat it under reflux with aqueous sodium hydroxide. So let's write that down. So heat reflux with sodium hydroxide. So when you do that, let's put our 3 sodium hydroxide molecules in there. When you do that, let's say draw our product molecule down here. We're going to remake the glycerol molecule, which is the backbone like this, with our H2 there, and our hydroxyl groups instead of our, and they become the ether links in the reverse direction. So that's our triglyceride, and we also get 3 fatty acids, which are, we actually get 3 salts, so 3 of. Alright, so if you've used sodium hydroxide, you're going to get a sodium ion there, and you're going to get this carboxylate ion here. So that's going to be the oxygen with the minus charge. And the rest of our chain we can summarize like so. You're going to get 3 of those. And this is the interesting molecule here. Alright, so it's a sodium salt, sodium from the sodium hydroxide, and the anion is the carboxylate ion that we've hydrolyzed. And this is soap. That is soap. And you can see it's ionic there, and that's what makes soaps solid. And that's how you make soap. With this glycerol here, we've got glycerol as a byproduct, and that's sold. It's got value, and pharmaceutical and cosmetic industries buy glycerol molecules from soap manufacturers. So there you have it. So as well as fats and oils being esters, biodiesel is actually an ester as well. So biodiesel is an ester. So biodiesel is mostly made from rapeseed oil. So rapeseed oil here, and in order to turn it into biodiesel, you have to do some work on the rapeseed oil, because rapeseed oil is a triglyceride like the ones we saw in the previous slide, and that as it stands is too viscous. It doesn't run or flow easily enough to make it combustible enough to use in a combustion engine, right? So in order to make it less viscous, more runny, we need to split the triglyceride up into 3 separate esters, right? And that reaction there is called a trans-esterification reaction. Trans-esterification reaction. It just means splitting the 3 fatty acids that are combined together in the ester that comes out of rapeseed oil. So that's like 3 in 1, right, to 3 separate esters. Let's have a look at doing that now to make it clear. So let's draw out our rapeseed oil first. Rapeseed oil is, like we said, it's a triglyceride, so we're going to have this 3 vertical carbon backbone, which we can complete with our redundant hydrogens like so. Then, as you remember, we've got our ester links. Let me just make that ester link nice and neat. And next to the ester link, of course, is our carbonyl group. And then the alkyl group of our fatty acids, which may be the same, may be different, about 18 carbons in these alkyl groups. And this esterification, trans-esterification reaction involves using methanol, CH3OH, and when we react that with a sodium hydroxide catalyst, then what we do is we split up that triglyceride into 3 separate esters, and the 3 separate esters look like this. So you can see that's come from the top, part of the triglyceride molecule. The other ones look the same, except our alkyl groups may be different. And these are the biodiesel esters. These esters here are the biodiesel esters. And let's not forget that we're going to remake glycerol, because it's glycerol that has been eliminated from this reaction. I'm just going to type over my picture there. Here's our glycerol. And that's what's happened. So glycerol, the biodiesel company would sell off to probably the pharmaceutical industry. Biodiesel is going to be added to normal diesel and sold to oil companies to allow us to burn in our cars. And so there we have it. That's a trans-esterification reaction, splitting the 1 triglyceride up into 3 separate esters using the sodium hydroxide catalyst. So that's the end of this lesson on esters. As usual, let's just check that we've done everything we wanted to do. What are esters? Well, we know that they are molecules that combine acids and alcohols. And we looked at those esterification reactions, both in the forward and the backward directions. Uses, we had the 4 uses of esters. And then we looked at hydrolysis of esters, both acid and alkaline, making the 2 different products there. Then we had a look at fats and oils, which are types of esters. In fact, we alkaline hydrolyzed beef fat and made some soap out of it. Okay, so all done. Hope that's been clear.